All right, welcome to section 9.7 part 1. This one is called using trig identities. This is a fairly difficult, fairly challenging section. Part 1, not so bad because we should know how to do it, but part 2 and part 3, it gets a little challenging. That's why I kind of put this funny little meme here. So the essential question for part 1 or section 9.7 is, how can you verify a trig identity? And that won't really make a whole lot of sense because you really don't know what a trig identity is yet. Okay, so we'll move on from there. What you're going to learn in this first part is use trig identities to evaluate trig functions and to simplify trig expressions. Okay, so that's what we're going to do in this first video installment of section 9.7. We'll talk more about this joke as well. Hopefully that makes sense to you, and this will make more sense once you see your trig identities. And now this video has two parts. Part 1 is finding trig values using old knowledge. So we're going to use things that we already know to solve things that we haven't done yet. Okay. So the first thing we need to be able to do on this first example that we're going to look at is we have this trig identity / function sign charts. Okay. So the three I'm going to talk about are sine, cosine, and tangent. Okay. So the first one, and I think we've done this. I think we've done this before. But first thing I'm going to talk about is sine, and we know that sine equals y values. Then the second one is going to be cosine, and we know cosine is x values. And then the third one is tangent, and we know tangent is y divided by x. Okay? So all we are doing on this first page here is we are going to figure out where is sine positive and negative, cosine positive and negative, tangent positive and negative. Okay, so let's think about this. If sine is equal to y, where are y values positive? Hopefully you know above the x-axis, y values are positive, and below the x-axis, y values are negative. So if that's the case, that also goes for sine. Sine is positive above, negative below. Cosine deals with x values. So where are x values positive? Well, x values are positive to the right of the y-axis, so positive in the first and the fourth, and negative to the left of the y-axis, so negative in the second and the third. Tangent, however, now is y divided by x. So we're going to take our y and divide it by our x. So let's look at the first quadrant. Positive divided by a positive is a positive. Second quadrant, positive divided by negative is a negative. Third quadrant, negative divided by negative is positive. And then fourth, negative divided by positive is going to be a negative. So tangent is positive in the first and the third, negative in the second and the fourth. Okay, so we're going to need to use this information in order to solve our first example. All right, so example 1. Given that sine of theta is equal to 4/5, we already know one answer. Sine is equal to 4/5. We automatically know now that cosecant is equal to 5/4 because they're reciprocals. And I didn't even need to look at anything. I automatically know that if sine's 4/5, cosecant's 5/4. And then the rest of the question says find the other 5 trig functions. Well, we've already found one, so now we have 4 to go. Okay. So this new piece of information here tells us what quadrant our angle is located in. So if we go back to think about the unit circle, here is 0, here is pi over 2, there's pi, down here is 3 pi over 2, and then we finish up at 2 pi. So this dot right here is for 0 radians and 2 pi, pi over 2, 1 pi, 3 pi over 2. All right, so let's see where theta is. It says theta is less than pi, so smaller than pi, so going up from pi, but it is bigger, so this part says it's bigger, theta is greater than pi over 2. So here's pi over 2. So if it's greater than pi over 2 but smaller than pi, it's got to be in the second quadrant. So our angle is going to be in the second quadrant. All right. So now what am I going to do? As soon as you find out what quadrant you're in, you're going to draw your triangle. Okay, so how do I do that? Okay, you just draw a triangle just like your note cards. You're going to draw a triangle in the second quadrant. All right, now what else do we know? All right, let's see what else we know here. They gave us sine, and we should remember that sine is opposite over hypotenuse, or y over r. Okay, so remember theta is always the one nearest the origin. So we know that our opposite side is 4. So opposite this angle is 4. And we know our hypotenuse has to be 5. So across from the 90 is hypotenuse. Okay. So what does that make us need to do here? So basically what we need to do is we need to find our third side. So I'm going to do the Pythagorean theorem, a squared plus b squared equals c squared. We only know one of our legs, so I'm going to do 4 squared. We don't know what b is, and our hypotenuse is 5 squared. So we have 16 plus b squared equals 25. And subtract 16, so b squared equals 9. Square root both sides, I get 3. Square root of 9 is 3. Now, here's the tricky part. The square root of 9 is 3. However, this side here is going to the left, so it has to be a negative 3. Okay, so it's going to the left. So 4 is going up, so it's positive. Hypotenuse is always positive. This is going to the left, so it has to be a negative 3. All right, so we have sine, we have cosine, cosecant. We have to do cosine. So let me change my pen color here. We need to find cosine. We need to find tangent. We need to find secant. And we need to find cotangent. All right, to finish this problem up. All right, so let's see here. So cosine. What is cosine equal to? Cosine is adjacent. So if you need to write down SOHCAHTOA, S-O-H-C-A-H-T-O-A. Cosine is adjacent over hypotenuse. So adjacent is negative 3, hypotenuse is 5. And that would make my cosecant negative 5/3. And then tangent is opposite over adjacent. So opposite is 4, adjacent is negative 3. So negative 4/3, which would make the reciprocal negative 3/4. Okay? So basically, we've just used old knowledge to be able to figure out where the triangle is and then being able to list. So as soon as you know one, you should know 2 automatically, and then you need to find the other 4 that they don't give you. Okay, we'll do another example in class tomorrow, but that is part 1 of this video. All right, so part 2. This is where it gets a little dicey, a little bit challenging. Okay, this is called using trig identities to simplify expressions. And right now, you don't have any idea what a trig identity is. Okay, but let's use what we already do know. Okay. So I have this blank unit circle here. Okay, I have a blank unit circle. And I know that if I put a point on my unit circle, I'm going to label this x comma y. Okay. And if I draw a line to the origin and then a line straight down, I have my right angle. Okay. We also know that cosine is equal to x. So whatever your x value is, that's your cosine. Sine is equal to y. Okay, so here's my x, here's my y, and then remember, if this is a circle, then this side is equal to r. Okay, and on the unit circle, what was the radius of the unit circle? Remember, this one was 0, 1. This point over here was negative 1, 0. This point was 1, 0. This point was 0, negative 1. So the radius of the unit circle is 1. So the radius is always 1. Okay? So that is just common knowledge that we've learned from the unit circle after doing trig for so long. And we can also write this x squared, okay? X squared plus y squared. So your x value plus your y squared is equal to 1 squared, or just 1. Okay? If the radius of the unit circle is always 1, x squared plus y squared has to be 1 squared. Or I can rewrite this. If cosine is equal to x, this could also say cosine squared. And if sine is equal to y, sine squared equals 1. Okay? So now this formula here is called a trig identity. It's an equation that's true for everything. Okay? And if that didn't make a lot of sense, then we'll talk about that more. But this is where these trig functions come from, the unit circle. Okay, so we have one definition. A trig equation that is true for all values of the variable for which both sides of the equation are defined is called a trig identity. Trig identity. So I've supplied you with a list of all of the trig identities we're going to talk about. And the list is broken up by name. So we have the reciprocal identities, cosine, cosecant goes with sine, secant goes with cosine, cotangent goes with tangent. We have the tangent and cotangent identities. Tangent is sine over cosine. Cotangent is cosine over sine. We have the Pythagorean ones. This one is very important. So these you're going to use a lot. Tangent and cotangent you're going to use a lot. These are the two main ones. Okay. The other ones are important. They're just not as common as the other ones. So we're going to use these. You have a sheet. Okay, so when you use this sheet to do the examples. Okay, so example 2. Use trig identities to simplify the following expressions. Now, I haven't written the problems down yet. These are the 2 ideas, though, that you're going to want to take with you. There are a couple different things you can do to solve these. Solving 1. Try to turn everything into sine and cosine. Okay, we're going to do a couple like that. If that doesn't work, there's a way to try to turn everything into the same trig function. So if you can turn everything into the same thing, you've simplified that as well. Okay, so basically we're simplifying, not solving. I should not use the word solve. Okay, so what do these look like? Okay, so you're going to need to flip back and forth from your chart that I gave you to the problems. All right, so let's see. Okay, so we're going to try to turn everything into sine and cosine. That's your first thing you're going to try to do. All right, so this part right here, is this located anywhere on your chart? Tan of pi over 2 minus theta. Okay, let's find it. Is this anywhere? Tan of pi over 2. Okay, here are your cofunction ones. So if you see here, tan of pi over 2 minus theta is equal to cotangent of theta. So I'm going to write, instead of this, I'm going to write cotangent. We've simplified that a little bit. Okay, so this part right here is equal to cotangent of theta. And we still now have sine of theta. I'm just going to bring that down. All right, so we're almost getting things into sine and cosine. Now, is there anything I can turn cotangent into that looks like sine and cosine? So I'm going to go back. I'm going to find cotangent. This one right here, but it's equal to 1 over tangent. That's not going to work. Here's another cotangent. It says cotangent equals cosine over sine. So I can turn cotangent into cosine over sine. That's what I want to do. I want to turn everything into sine and cosine. So this cotangent, if I follow that rule, says cotangent is equal to cosine over sine. And I'm going to leave off the thetas for now. And we're still multiplying this by sine of theta. Now I'm going to put sine of theta over 1, so I have 2 fractions. Okay, what can I do here? Well, I have a sine over sine, those cancels, and I'm left with cosine over 1, which is just cosine theta. So this whole thing simplified all the way down to cosine. Okay? All right, let's look at the next one. We're going to try to turn everything into sine and cosine. Okay? All right, so let's see here. The first one is already sine, so I'm just going to bring that down. So sine of x, I'm going to put parentheses around it. Cotangent we just did. What was cotangent equal to? Cosine over sine. Cosine over sine. And I'm going to put the next one in parentheses, secant. Is there any formula that will turn secant into sine and cosine? So let's go back. Is there any way to turn secant into cosine and sine? I don't see secant anywhere here. Here's one right here. So secant is equal to 1 divided by cosine. So there we go. We've turned secant into something that's sine or cosine. So secant is equal to 1 over cosine. And I'm going to put sine over 1 just so they're all friends, they're all fractions. Okay, so let's see if there's anything we can cross off. Oh, now I forgot to put the x's. You can put the x's here. That really doesn't change the problem. All right, so let's see what we have here. We have sine over sine again. Those cancels. And we have cosine over cosine, so that cancels. So all that's left is 1 divided by 1, which is 1. Okay, so we use these trig identities to simplify the expressions. All right, let's try 2 more. All right, so let's see here. Here we have secant of x times tan squared of x plus another secant of x. So if we notice, we have 2 secants and 1 tangent. So I'm going to try to, instead of doing everything into sine and cosine, which you can try, but you'll kind of run into a dead end, I'm going to try to do number 2. We're going to try to turn everything into the same trig function. So if we already have 2 secants, let's try to turn everything into secant. So I'm going to bring this secant of x down, and we're going to try to turn tan squared into something with secant. Okay, so let's see if we can do that. Let's go back to our chart. Get rid of everything that's here. So I don't have any tan squared. There's no tan squareds here. So no tan squareds here. None here. None here. None here. None here. I don't see a tangent squared here. I don't see tangent squared here. None here. None here. None here. No tangent squared anywhere here. However, here we go. I have a tan squared in this problem. So I'm probably going to need to do this one. Well, I need to know what tan squared is equal to. So how would I get this 1 on the other side? If I subtract 1 from both sides, I now have tangent squared is equal to secant squared minus 1. And what do you know? I've turned tan squared into something that has secant in it. And that's what we want. We want we want to turn tangent into secant. So secant squared minus 1 is equal to tan squared. So tangent squared is equal to secant squared minus 1. All right, so we've turned everything now into secant. We've done number 2, try to turn everything into the same trig function. So now we're just going to simplify. Secant times secant squared is secant cubed. Secant times -1 is negative secant. And then at the end here, I have a plus secant to finish off my problem. All right, so I don't have any other cubes, so I'm just going to bring that down. I'm going to add the x to it since we had x's at the beginning. Now notice what do we have here? A negative secant plus secant cancel out, so my final answer is secant cubed. Okay, little challenging. I'm not gonna argue with it. These are a little bit difficult. That's why we do it kind of at the end. Last one here. So we're going to turn everything. We're going to try to turn. We have 3 different trig functions, so therefore I'm going to try to turn everything into sine and cosine. Okay, tangent from your chart. Let's see what tangent's equal to. So tangent right here is equal to sine over cosine. So tangent is equal to sine over cosine. I'm going to put my big fraction mark. What is cosecant? Cosecant right here is equal to 1 over sine. So I'm going to write 1 over sine times 1 over sine. And then now what is secant? Secant is 1 over cosine. So I'm going to write 1 over cosine. So on the bottom, secant is equal to 1 over cosine. All right, so let's simplify what we have here. On the top, I'm only working with the top. Sines cancel. I'm left with 1 over cosine is equal to 1 over cosine on the bottom. So let's use a little bit of logic here. 1 over cosine divided by 1 over cosine. Cancel. I'm left with 1. So all of that work right here simplifies to 1. And we use our trig identities, which is all of these formulas, to simplify these problems. All right, thanks for watching. This is a little bit difficult, but we're going to do more examples later. See you tomorrow.